yesterday. All right. So, today we are just talking about more ways that you can model exponential scenarios. So, yesterday we talked about exponential growth and decay. So, just as review, can anyone tell me what the formula is for exponential growth? Landon.
Y equals a 1 minus one minus r squared.
Close. So you were kind of leaning more towards decay. It's actually 1 plus r for growth. So it's y equals a, or you may see it as p for principal, 1 plus r raised to the t power. And decay is the exact opposite. So it would be y is equal to p 1 minus r to the t power, where p is your initial value or your principal, r is your rate of increase or decrease, and t is your time. Now, we're going to learn about a couple of other ways that we do exponential functions. So, first off, we can model many physical phenomenon if we know their percent increase and decrease per time unit. So in this lesson, we'll learn about more flexible with our exponential modeling. So we're going to still be using these two formulas, but we're kind of going to do more manipulation to them. All right. Guys, make sure you got your packet out. Yeah. All right. So let's look at this first exercise. So a colony of fruit flies has a population that doubles every 8 hours. There were originally 22 fruit flies in the population. All right. So let's go through these questions because it'll actually help us set up what they're trying to look for in this case. So this is what we call a doubling problem. So if P represents the population of fruit flies and D represents the number of times the population has doubled, write a model for P as a function of D. So P is the population, D is the number of times the population has doubled. So for example, if they started with 22 and they doubled once, how many would you get? 44. Double again. 88. Double again. Yeah, something like that. All right. So let's write a formula for this. So we're not necessarily using. Actually, we are. So would this be kind of an exponential growth or an exponential decay problem if we're doubling the population? Growth. So that means we're using the a 1 plus r to the t power. All right. Now, let me ask you this. We know we started with 12. So we know our initial value, or not 12, 22. We know our initial value is 22. We know our time will just be replaced by d because that's just how many times it doubled. However, what do you think my rate's going to be if we're doubling? Not 0. So think about it. If we're doubling the entire population, all right, that means what percentage are we increasing by? You're close. We're increasing by a rate of 100%. So it should be that when your rate would be 100% or 1. So what's going to happen is when we plug it into this formula, all right, everything in, we should get P is equal to 22 times 1 plus 1 raised to the d power. Or in this case, P is equal to 22 2d, where 22 is where we started at. 2 represents that we're doubling, and D represents how many times we did double. What's up?
You still have good cardio one for me.
Oh, Lord.
Yeah.
I forgot we got to end that session. Well, it's half day, so my scheduling is off. All right. So now this is the equation that we're looking for and what we're going to use to describe a lot of different things. Now, if H represents the number of hours since the population was originally at 22, what is the equation that relates H to D? And we're going to solve that in terms, and we're going to solve for D in terms of H. All right, so first off, how many hours does it take for the population to completely double? What does the problem say? 8 hours. All right, so every 8 hours. So that means that, yes. So that means that every 8 hours, we double one time. So if we're going to solve D in terms of H, all right, D is one double. So every 8 hours, we have one double. But let's think about this. How much will we double in the span of 1 hour? How much do you think? So if it takes 8 hours to completely double, how much of the double will be completed in 1 hour? 1/8. So 1/8 of the double will be completed in 1 hour. All right. Now, the reason we wanted to do that is because if it takes in 1 hour, if it takes 1/8 of the double, if we want to write this in terms of doubling, all right, that means that we would have to figure out how many hours, if we take the number of hours and then divide it by 8, that's how many times we actually doubled. So in 1 hour, it takes 1/8 of a double. All right. So if we want to solve for D, all right, so we don't know how many times we're doubling or if we're doing a complete double, if we're doing it based off of hours. So like I said, we probably have to divide H by 8 so we know for certain how many times that doubling happened. So for example, if 32 hours passed, how many times did I double? 4. Now, if 30 hours pass, how many times did I do a full double and some change? So about 3, and then there's some change. All right, so that's why we got to divide by 8, because we know that they're not going to be always nice hours. All right, so then what's going to happen is, since D equals H divided by 8, because we know that H is equal to 1/8 of D, all right, H is equal, or 1H is equal to 1/8 of D. All right. So in order to figure out, based off of your hours, Okay, I'm not going to go into more detail with that because I'm going to confuse myself and confuse you. Just know that D has equals to H divided by 8. All right? Because we want to know the hours and how many times they double within those hours. All right? So we got to divide it by 8. Divide the hours by 8 to figure out that after 8 hours, every 8 hours we double so many times. We need to figure out how many times that doubles, and to do that we divide by 8. I'm going to leave it at that. All right. So now we're going to use our answer from A and B and write a model for the population of fruit flies in the terms of number of hours. So all we're going to do is replace the D in this function here with what we got here. All right. So this would be P is equal to 22 times 2 all over H divided by 8. So in other words, if we were given the number of hours, that means that we can easily figure out how much we doubled within that number of hours, or what percentage that we doubled. Because then it asks, by what percent is the fruit fly population increasing per hour? So we want to know our percent of increase. So per hour, all right? Now, all right. So we know, yes. Yeah. So we know that we do 1/8 of a double in 1 hour. So 1 hour equals 1/8 of a double. All right. So if we're doing 1/8 of a double, what's 1/8 as a decimal? Because we need to convert it to a percent. So does anyone know off the top of their head? So 1/8 as a decimal is 0.125. All right. So what's that as a percent? 12.5%. So we're increasing by 12.5% increase per hour. That's how much we are increasing for our hours per hour. All right. Well, it's a lot of different parts. So basically, what they're trying to get at is with doubling, you're typically going to have a base of 2. All right. So the base of 2 always means to double. And then, depending on what units they give you of time originally, you can manipulate your exponent in terms of time to reflect the units that you're given. Because sometimes they may say, like, they double every 2 hours. So, what is that in terms of minutes? Like, however they say it. Sometimes you have to convert and to be able to get the correct units of time. So, you got to kind of go around your butt to get to your elbow a little bit. All right. So as long as we are careful when we set up our models, so we just have to be very careful when we set up our models, we should be able to move from one unit of time, like doubling, to another unit of time, like hours. All right. So it kind of takes a little bit more out of the box thinking a little bit. Now let's try another one. So with radioactive material, it has a half-life of 35 years. If A of 0 represents the original amount and at present, and T represents the number of years it has been decaying, which of the following models the amount A of radioactive material still present after T years? So let's talk about this. So has any of you guys taken chemistry yet or physical science? All right. Do you guys remember talking about half-lives? Like kind of what that means? So for those of you who don't know, half-lives are when you take a radioactive material like say plutonium. And when companies try to dispose of it by either burying it or whatever, it takes that many years for it to become less and less radioactive. So basically it'll cut whatever's going on in half. All right. So that's what half-life means. So that means that after 35 years, if we started with say 200 milligrams of material, how much will we have after 35 years? 100. It cuts it in half. So when we talk about half-life, we're decreasing by 1/2. All right. So looking at our 4 answer choices, if we're decreasing by 1/2, so our rate of decrease is 1/2, what 2 answer choices can I go ahead and eliminate? 3 and 4. Because 3 and 4 are talking about what? Doubling. So 3 and 4 are referring to doubling because it has a base of 2. So these refer to doubling. We're looking for a base of 1/2 because that means it's being cut in half. Now, we're looking for when T is years, we're looking for how to represent T in terms of 1 year. So in 1 year, what fraction of the half-life would have already happened in 1 year? So it takes 35 years to do a complete half-life. So in 1 year, how much has happened in the half-lifing process? 1 out of 35. So in 1 year, we've done 1 out of 35 of the half-life. So if T represents years, or in this case, 1 year, which of those 2 answer choices do you think you would pick to represent our equation? 2. Because essentially we're saying that if we're given so many years, we need to divide it by 35 so we know how much of the half-life cycle we've done. So for example, if only 3 years have passed since we've done the half-life, we would put 3 in for T, divide it by 35, and that's how much of the cycle we've done. All right, so basically your exponent is talking about how much of the cycle you've done. All right. Does that kind of sort of make sense? Yes, no, maybe so. All right. Now, we're going to use that correct model from exercise 2. And if we replaced it in the form A of T equals A of B to the T form, then what would be the value of B accurate to 4 decimal places? So essentially what that means is that we can break apart. We're going to be doing some power rule stuff. So we're just going to rewrite what we had for number 2. So we had A of T is equal to A subset 0 of 0.5 times T to the 35. Subset 0 or sub-0, whatever. So let me ask you this. It wants it in terms of 1T. So we're trying to figure out A of 0 times what base raised to the T power. So we want to get rid of the division by 35. That's what we're looking for. Now, what can I do How could I rewrite this exponent t over 35? So I essentially want to separate the t and the dividing by 35. How do you think I would do that? Not necessarily. I just want to separate the two into two distinct values. How do you think I can do that? Let me ask you this. Is t over 35 the same as 1 over 35t? Yes. That's what I'm looking for. I'm going to replace this with this. So I would get a of 0 times 0.5 times 1 over 35t. Now what I can do is that we can do the power rule with the 1 over 35 to break apart the 135 and the t. Does anyone remember what the power rule means? Landon. So it's one of the exponent rules. So just to remind you guys, essentially what the power rule is that you take the number and you multiply it to every base within the parentheses. You multiply the exponent by every base in the parentheses. So if 0.5 is an exponent 1 times 1 over 35, this now becomes 0.5 raised to the 135 raised to the t power on the outside. So this is just a number. So if we put that in our calculator, we should get our actual rate of decay. All right? Because remember, exponential decay is a equals p of 1 minus r raised to the t power. All right? We're trying to figure out, one, what our rate of decay is, but two, what percentage we're actually decaying by. So if we put this in our calculator, we would get a b value equal to, and just to save time, I'm just going to give it to you, 9804, and that's a rounded answer. All right. So this is actually our decay factor. It's not the rate of decay, it's our decay factor, meaning that every year, if we multiply our original value by 0.98, it would give us what we have left after that year of a half-life. So we would put 0.9804 here. Now, I want to find my actual rate of decay, so my R value here. How do you think I would find that? Using this formula and this value? What do you think I would do? So let's look at it this way. If 1 minus R is equal to 0.9804, then what can we draw from that conclusion? So if 1 minus R equals 0.9804, what conclusion could we draw from that? Couldn't we say that 1 minus 0.9804 is equal to R? Would that work? Yeah. Because essentially R plus 0.9804 is equal to 1. So all we had to do was switch these two to get our R value. So if we do that, we should get R equals 0.0196. So what's that as a percentage? So what's 0.0196 as a percentage? Close. 1.96, because you're moving only 2 decimal places. So be here. So that means we are decaying at a rate of 1.96% per year. So if we're looking at our half-life, it may take 35 years for the half-life to go in effect, but if we go year by year, we will eliminate 1.9% of the material every year. Yes. Yeah. Any questions on that? So guys, they're trying to make us go in kind of a roundabout way. Essentially, if they ask for it in terms of 1T or 1 year, just take whatever you're dividing by, convert it into a fraction, so like 1 over whatever that number is, and raise it to whatever your base is. So 0.5 to whatever. All right, let's do one more. So it's fairly common to move between time units such as days, weeks, hours, etc. So the number of people who know a rumor as a function of days since it started is given by this function here. We want to write a model for the number of people who know the rumor as a function of the number of hours since it has been spreading. And then it also wants to know at what percent to the nearest tenth is the rumor growing per hour. So first off, would you think of this problem as exponential growth or decay? The function that they give us is not an exponential growth or decay function, but what will be kind of our end goal here? Growth. So we're talking about growth here. All right. So first things first, we need to convert this function from days to hours. So let's talk about this. If we're looking at days to hours, how many hours are in a day? 24. All right. So if we're going from days to hours, 1 day equals 24 hours or 24H. So that means that 1 hour H is equal to what? In terms of days. So from that first equation, how do I get the H by itself? I would do what? How do I get this H by itself right here? Divide by 24. So I would divide both sides by 24. So that means in 1 hour, we have it by D divided by 24. So then we're going to take this and plug it in for the D here. So we have 5 times 3.8 all raised to the D over 24. Now, they want this in terms of 1 hour. All right. So I want to be able to say that 1 hour has happened. So essentially, we're going to say 5 times something, and then we'll be able to raise it to the H power. All right. So if I want this to be raised to the H power, how can I get rid of the divide by 24? What did we do in the last problem to get rid of the divide? Right. We're going to raise this 3.8 to the 1 over 24 because we want to know what that rate is for 1 hour. So 1/24 of the day gives us 1 hour because this rate, 3.8, is over the course of 1 day. This rate, 3.8 raised to the 1/24th, is over the course of 1 hour. That's what they want to know. All right. So if we put that in our calculator, we should get 5 times 1.06 raised to the H. So if exponential So this is our function in terms of hours. So we can say n of h is equal to 5 times 1.06 raised to the h power. So this is our function. All right. Now, how do I get my actual rate of growth from this function? So remember, exponential growth is a equals p times 1 plus r to the t power. So essentially, our rate of growth, or r value, is going to come from this term here. How could I figure out what that r value is? Does anyone know what the r value is? So this number right here represents 1 plus r. And that comes straight from our formula here. So guys, what's our r value? 0.06. All right. If we put this as 1 plus 0.06, we should get 1.06. All right. So that means that as a percent, r is equal to 0.06. So as a percentage, how much are we increasing per hour? 6% per hour. All right, you guys have to be very careful with that. All right. So really think about these problems really require you to think outside the box when you're converting. So like from days to hours, think about how many hours are in a day. How would you represent that in terms of 1 hour? Mm-hmm. Or if you're going from hours to minutes, think how many minutes are in an hour. How would I convert from hours to minutes or from minutes to hours? All right, that's just something that you got to think about while you're doing these. Any questions? All right, so I'm going to stop there for today. We'll pick this up on Monday with 2.2C. So no new classwork for right now, unless you want to start your packet work for 2.2B, which is pages 7 through 8. All right, besides that, you can continue to work on your intro to Unit 2 Delta Math. Remember, that's going to be due Monday. And that's pretty much it. And then here's your exit ticket for today.